Okay, go ahead.
Hi, we are here with Summit Engineering, and we're here to present the Riverstone Rise project proposal.
It's the bottom button.
Okay, thank you. This is our table of contents. First, we're going to start with the project description. Then we're going to move on to structural criteria. Then the floor framing system, lateral load system, foundation systems, material takeoff, and we finish with a conclusion. First is a project description. Our mission statement is, at Summit Engineering LLC, our goal is to design innovative, sustainable, and structurally sound solutions for our clients. Collaboration, integrity, and perseverance are core values in our firm. Now we're going to introduce our team.
Yield strength of 50 KSI, and then you can see all our property data for like the slab depth, the rib depth, stuff like that. So we have a fire rating of 2 hours, and we used 3-inch metal and 4.5-inch concrete for a total depth of 7.5 inches. And you can see here we used 18 gauge, and that's our fire rating. For the first floor, here's our moment and shear diagrams. Yeah, pretty self-explanatory.
Thickness of 24-inch, which is 2 feet, and 9,000 psi for the wall. And for the upper half, since it's lighter, smaller, we had 8,000 instead with the 20-inch thickness. Upon running the analysis, we realized that we have a really weak axis, and that's as a rectangle, it's the longer side. That means we have to actually add an outrigger to make sure we have enough stiffness to manage the deflection criteria that we have. Here you can,
Sorry.
You're good. Here you can see that I actually had to change the beams from down here all the way to the maximum in order to transfer the load down to the foundation. So deflection summary. This is the white displacement. It's just under 12 inches. X displacement, that's the strong axis, so we have it at really low values. And this is generally the summary that we got from ETABS after doing our analysis. Story shear due to the wind. There is, right here, you can see that there is a huge change. This is because we added the outrigger, and the stiffness and everything will just be transferred downwards, hence the very difference right here. Right here on the overturning moments, you can see something similar. Around floor 26, 24, you can see that we have this weird jagged edge on the graph, and that's due to the outrigger as well. For the wind displacement, this is just very similar to the summary that I put on Excel earlier. Shows how much displacement we have, just all combined into one graph. You'll see that on the next slide, we have the H over 500 design criteria. Our building is 600 feet. So if we convert that to inches, that's 7,200, which means our allowable deflection is 14.4 inches. Since we have a 12-inch and I believe 5-inch, 4-inch max displacement, we are good. So going on to the foundation system, we are using a reinforced concrete design. Foundation that we have is a mat. Our soil has 20 kips per square foot for the allowable soil bearing capacity, and we're using a subgrade modulus that computed at 480. Here we also notice that we also have a 150 feet by 210 base. That will later come into our calculations due to material takeoff. And we're using 6,000 psi concrete as well as a 9-foot thick mat. This is the load case that we're using. Perfect. So this is what I basically recommended for each of the cases. Since on the outer edges, we don't have all that much stress. We could get away with 12 inches, 9 inches on the top X direction. On the Y direction, we also have like 9 inches, number 11 on the top, with the bottom with number 11 on the bottom. Since the bottom typically holds a little bit more significance, they're more closely knit together. For the core wall, since it's not really ideal for us to be utilizing 3 inches spacing, since that makes workability and constructability all that more difficult.
We had to scrap the old design because the column strength wasn't like good enough, and also we just wanted to like better the visual appeal of the building. Also, we had some trouble with the 3D model because like trying to export it, like the 3D model was way too big, like to print in 3D print in time. So we just made it out of wood. Laser cutting and all that. Some of the lessons we learned were we obviously learned how to use ETABS, and then we learned how to design using various codes, and then we also were able to like observe the behavior of the building under different loads, specifically this year in the moment, and how like specifically like how different floor plans would impact the forces. For example, like Jason was saying, like right where the floor plan changes, like we had to include the outrigger system because like shear was too big. And that's it.
All right.